Welcome, my friends. I'm so excited because in this video we get to talk about the confidence interval for the mean and all the details of how this confidence interval is constructed. So let's go ahead and get started. Now, the purpose of finding a confidence interval for the population mean is to estimate the population mean. We typically don't know the value of the population mean because that would require a census to calculate. We would have to have all the data for everyone in the entire population. So instead of taking a census and calculating the mean exactly, we're going to take a sample and calculate the sample mean. But the sample mean's most likely going to be off by a little bit. It's probably not going to be exactly the same as the population mean. So we're going to add and subtract some margin of error to create an interval to which we can be, let's say, 95% confident that the true mean falls between. To do this, we can use this formula. We will take the sample mean, oftentimes called the point estimate for the mean, because it is our best estimate for the population mean, and then we will add and subtract the margin of error. The margin of error is made up of a t-score from the t-distribution, which we'll talk about shortly, s, the sample standard deviation, and the square root of our sample size. Here are all the values in the formula defined. X bar is the sample mean, t is the t-score from the t-distribution, s is the sample standard deviation, and n is the sample size. As I mentioned a moment ago, we call the sample mean x bar the point estimate for the population mean. This just means it's our best estimate for the value of the population mean. The whole point of the confidence interval is to estimate the population mean, which we wouldn't know unless we had a census. Since in most cases we will not have a census, we got to settle for the next best thing, which is a sample. From the sample, we will calculate a sample mean, which is our best estimate for the population mean, and then we'll add and subtract the margin of error. The margin of error is everything after the plus or minus, which includes the t-score, the standard deviation, and the square root of the sample size. Sometimes we just refer to this as the error. On the number line, the confidence interval looks something like this. The point estimate, or in this case, x bar, will always be in the center of the confidence interval. And then we will have the lower bound somewhere to the left and the upper bound somewhere to the right. The distance between the sample mean, either to the upper or lower bound, is the margin of error, which can be found by t times s over the square root of n. This picture exemplifies the formula. We take the sample mean and we add and subtract the margin of error. Add to get to the upper bound and subtract to get to the lower bound. The final interpretation of this interval would be we are some percent confident, such as maybe 95% confident, that the true population mean falls somewhere between our lower and upper bound. All right, the next thing to talk about is this t-score. So where does that come from? Well, you may remember that we have something called the z-distribution, which is just a normal distribution with a mean of 0 and a standard deviation of 1. So visually, the z-distribution looks something like this. 0 right down the middle with a standard deviation sigma equals 1. In this section, we're going to be using a t-distribution, which is very similar to the z-distribution. It also has a mean of 0 and a standard deviation of 1, but it's going to be utilizing the sample standard deviation, since we're going to be using a sample to construct our confidence interval. So the t-distribution really looks very similar to the z-distribution, except for it is utilizing the sample standard deviation rather than the population standard deviation. Now, since the accuracy of the sample standard deviation is dependent on how big the sample size, it turns out that the t-distribution is going to look a little bit different depending on how large the sample size is. Technically, it varies based on the sample size minus 1, which is a quantity we call the degrees of freedom. As the sample size and degrees of freedom get larger, the sample standard deviation will be a better estimate for the population standard deviation. That means that the t-distribution is going to converge to a z-distribution as the degrees of freedom get larger. Here's a picture of the t and z distributions on top of each other for a very small sample size of n equals 6. Remember that the degrees of freedom are just the sample size minus 1, which are going to be 5 in this example. The z-distribution is in black and the t-distribution is in green, so you can see how close they are together. The larger the sample size and degrees of freedom, the closer these two distributions will be to each other. Let's look at the confidence interval formula to estimate the mean that we looked at from earlier. Let's talk more about this t-score. To find the t-score in the above formula, we need to use a function from the TI-84 calculator called inverse t. We can get to this function by pressing second, vars, and then inverse t on the TI-84 calculator. We'll do this together in just a minute. To use this function, we need two inputs. what are called the area to the left and the degrees of freedom. Let's look at an example. Let's say that the sample size is 21, which would mean that our degrees of freedom are 21 minus 1, which is equal to 20. Let's also suppose that we are using a 95% confidence interval. To use inverse t, you should always draw a picture of the t distribution. Here's what that might look like. If we have a 95% confidence interval, that's kind of like having 95% in the middle of our distribution. Since the entire distribution has to add up to 100%, that leaves us with 2.5% in each of the two tails, so that we have 95 plus 2.5 plus 2.5, which is equal to 100%. The t-score that we're searching for is the t-score on the right-hand boundary. We need the area to the left of the right-hand boundary, which is equal to 95% plus 2.5%, which is 97.5%. 95 and 2.5 are both to the left of the t-score, so we must add them together to find the area to the left. At this point, we found the two inputs into inverse t. We have the area to the left, which is 97.5%, and we have the degrees of freedom, which are 20. So we can head to the TI-84 calculator. On the calculator, press the second key, and then vars, which is the distribution menu for second, and then go down to inverse t. Press enter. For area, we put the area to the left, which is the area to the left of the t-score on the right-hand boundary of our distribution, which is 95 plus 2.5, or 97.5%. We need to put this in as a decimal, so we put in 0.975. The degrees of freedom are 20, so we put in 20. Go down to paste, press enter, and you will get the t-score of 2.086. The t-score that should be used in the confidence interval formula based on this situation would be 2.086. Note that if you have a TI-83 calculator, you will not have the inverse t function. You can program the function into your calculator by following this link and watching the YouTube video. Here are a few problems for you to try. Let's say we have a sample of size 30, and you were asked to find the t-score for an 85% confidence interval, a 90% confidence interval, and a 99% confidence interval. Pause the video and give it a shot. All right, hopefully you've given this a shot. I'm going to go ahead and solve number 1, and number 2 and number 3 should be very similar, so you should be able to do those based on my example. So let me go ahead and draw the distribution, because that should be the first step for any of these. So I can go ahead and draw a t distribution here with my mouse. Not too bad. And if we have an 85% confidence interval, we're going to draw kind of lines on the left and right hand side, and I'm going to have 85% in the middle. I'm going to represent this in a decimal form as 0.85, right? And that's going to leave me with some area in each of the tails. Well, how much area is that going to be? Well, 100 should be the entire thing, or maybe I'll do 1. And I can subtract the area in the middle of 0.85. That's going to leave me with 0.15, but that needs to be split evenly into each of those two tails. So I can divide that number by 2 to get 0.075. So each tail is 0.075. And that would also apply to this other tail, so that the entire area under the distribution is equal to 1 or 100%. Now the t-score that we're trying to find is the t-score on the right-hand tail. So we can go ahead and go to our calculator, go to second distribution, go to inverse t, and then for the area, we need the area that is to the left of this t-score. Well, that's going to be the 85% plus the 7.5%, which if my math is right, I believe is 92.5%, or 0.925. The most common mistake that people make is putting in the confidence level for the area. The confidence level is not the area. It is the area to the left of this value, which is the middle area plus the area in the tail. The degrees of freedom are always one smaller than the sample size, and they've told us the sample size is 30, so we should be using 29. So that means that the t-score for this example should be about 1.48. All right, go ahead and try the other two cases. They should be very similar, but you're going to have slightly different areas, and therefore your answer will be different. All right, hopefully you have finished all 3 of these here. The last thing to mention is, you may remember from a previous video, we said that there are 2 things that change the error in a confidence interval. The 2 things are the confidence level. If you increase the confidence level, that increases the margin of error. And the second thing is the sample size. If you increase the sample size, that actually decreases the margin of error. And now that we know the formula for the margin of error, which is t times s over the square root of n, we can directly see why that is. So if you've done this correctly, you should have seen your t-score get larger when the confidence level increased. And since the t-score is in the margin of error formula, as the confidence level increases, the t-score increases, and therefore the margin of error is going to increase, since the t-score is getting multiplied in the margin of error formula. So now we directly see why, as the confidence level increases, the margin of error increases. Well, because when the confidence interval increases, it increases the t-score, and the t-score is getting multiplied in the margin of error formula. Now we can also think about the sample size. We said as the sample size increases, the margin of error actually decreases. And the reason for that is because the sample size is actually in the denominator. If you increase the value of something in the denominator, then that term is actually going to get smaller, right? The entire thing is going to get smaller, right? So your margin of error is actually going to get smaller when the sample size increases because that sample size is in the denominator. Now, in order to create a confidence interval for the mean, there are a few assumptions that must be satisfied. First of all, you must take a random sample. So that means that there should be an equal chance to choose anyone in your population for your sample. Additionally, you must have either a sample size of n is greater than or equal to 30, or the variable should follow a normal distribution. You may remember that these were the conditions that were the case for the central limit theorem, and this actually is ensuring that the distribution of our sample mean will be normal by the central limit theorem. This needs to be true in order for us to use the t-distribution, which was in the formula for the confidence interval. All right, at this point, we are ready to work through a full problem. Suppose a random sample of 36 recent Grand Valley graduates found the mean student debt to be $20,000 with a sample standard deviation of $5,000. We are asked to find a 90% confidence interval for the mean student debt of recent Grand Valley graduates. The confidence interval formula for the mean is x bar plus or minus the t-score multiplied by s over the square root of n. The first thing you should do is write down all of the symbols related to the numbers that are given in the problem. We are given that the sample mean is $20,000, and that is x bar. We are also given that the sample standard deviation is $5,000, which is the value for s. The sample size is 36, which we represent by n. We're also going to need the degrees of freedom, which we know are n minus 1, or 35. Finally, we are given that the confidence level is 90%, so we can write that down as well. All right, at this point, we are ready to work through a full problem. Suppose a random sample of 36 recent Grand Valley graduates found the mean student debt to be $20,000 with a sample standard deviation of $5,000. We are asked to find a 90% confidence interval for the mean student debt of recent Grand Valley graduates. The confidence interval formula for the mean is x bar plus or minus the t-score multiplied by s over the square root of n. The first thing you should do is write down all of the symbols related to the numbers that are given in the problem. We are given that the sample mean is $20,000, and that is x bar. We are also given that the sample standard deviation is $5,000, which is the value for s. The sample size is 36, which we represent by n. We're also going to need the degrees of freedom, which we know are n minus 1, or 35. Finally, we are given that the confidence level is 90%, so we can write that down as well. From here, all we need to do is plug into the formula. We have x bar, which is 20,000, plus or minus the t-score, which is 1.69, multiplied by the standard deviation s of 5,000, divided by the square root of the sample size of 36. Let's head to the calculator to plug this in. I like to plug this in all at once to try to avoid any unnecessary rounding. So we can take 20,000, and then I'll do the plus first, plus 1.69. Now I'll just note I could have taken more decimals on the t-score, but generally I round this to 2 decimal places. But if you wanted to take more decimal places, that would be fine. Multiplied by 5,000, divided by the square root of our sample size of 36. Press enter and we will get the upper bound, which is 21,408.3 repeating. And then to get the lower bound, we can do the same thing, but just with a minus. But don't type it all in again. Instead, just press the second key and then the enter key, and that will bring up your previous answer. And then we can scroll all the way back to the beginning and change that plus sign to a minus sign. press enter, and you'll get the lower bound, which is 18,591.6 repeating. So here is that work separately for the plus and for the minus. At this point, the only thing we have left to do is to write our conclusion. And we're going to write our conclusion in the same general template that we used in the previous video. If you forgot what that general interpretation looks like, here it is. The general interpretation for a confidence interval is that we are C% confident that the interval between our lower bound and upper bound contains the, and then we're going to state either the population mean or proportion, depending on which type of confidence interval we are doing. In this case, we are doing a confidence interval for the population mean. So the way we can modify this for this example is, instead of saying C% confident, we would say that we are 90% confident that the interval between our lower bound, which was $18,591.67, and our upper bound, which is $21,408.33, contains the, and then we need to describe either the population mean or population proportion, and make sure that you adapt your explanation to fit the example that you are dealing with. So in this case, we would say the population mean, but we're going to be more specific. We're going to say the population mean student debt of all recent Grand Valley graduates. Now, let's take a step back and discuss the purpose of this problem. Now, the goal was to estimate the population mean student debt of all recent Grand Valley graduates. Now, to find that value exactly, we would have to have a census of all recent Grand Valley graduates, but most likely that's going to be pretty unrealistic. There's a lot of recent Grand Valley graduates. So instead, we have taken a sample of 36 of those recent Grand Valley graduates, and from that sample, we have found a sample mean of 20,000. Now, we know that our sample mean is probably not perfect. It's probably a little bit off from whatever the true population mean is. So that's why we call this the point estimate for the population mean. What we end up doing is we take that sample mean and we add and subtract a margin of error made up by the t-score multiplied by the standard deviation over the square root of n, and that's going to bring us to a lower and upper bound to which we can be 90% confident that the true population mean falls between. In this case, we don't really know what the true population mean student debt is, but we can be 90% sure that the true value falls somewhere between $18,591.67 and $21,408.33. This is the power of inferential statistics, which is all about saying things about the population based on samples. We had a relatively small sample here, only of size 36, and we're able to say with 90% confidence that the true population mean falls within a relatively small range. And I think that's pretty cool. Here's a problem for you to try. A random sample of 12 GRCC students who are enrolled in statistics this semester resulted in the following number of hours worked. Assume the distribution of hours worked for these students is normal, and we need that assumption in order to do the confidence interval because our sample size is not at least 30. We are asked to find a 99% confidence interval for the mean hours worked per week by GRCC statistics students. Now, the difference in this case is you are actually given the data. Remember, in the last problem, we were not given the data. We were actually given the statistics, like the sample mean and the sample standard deviation and the sample size. In this case, we're actually given the raw data. So if that's the case, then you need to go to your calculator and calculate those statistics yourself. So I will do that with you, and then I will let you try the rest on your own. So to calculate those statistics, we can go to our calculator, we can go to Stat, we can go to Edit, and then we can clear out our first list by hovering over the first list, pressing the clear key and then the down arrow, and then we can type all of these numbers in there. I'm going to kind of scroll down so we can see them at the same time here. So I have 6, 10, 15, 0, 7, 9, 22, 8, 16, 8, 5, and 12. And once you have all those numbers in there, you can go ahead and press Stat, arrow once to the right so that you're on the Calculate menu. Press Enter over 1 bar stats. Make sure it says List 1. If it doesn't say List 1, press second and then 1 to change it. Then go down to Calculate and press Enter, and you will have calculated the statistics. So the ones you're going to want to write down are X bar, because that's in the formula here, of 9.83. You will need S. They label it SX, but it's just S, which is 5.78, and then the sample size as well, which is 12. So use those numbers, and then go ahead and find the t-score. You'll have to use inverse t. We've already practiced that a few times. So draw the distribution with 99% in the middle, and find the t-score, and then plug everything in to get the upper and lower bounds to your confidence interval. Also, don't forget to write a conclusion or interpretation statement when you're done, and yeah, that should be it. All right, so I think that is everything that I wanted to talk about related to this video and the confidence interval for the mean. So hopefully you found it useful, and I will see you again in the next video.